So this YouTube outlines my final project, which is the simulation of tossing a coin. My objective for the coin toss simulation was to study the probability by counting the relative frequency of a type of event. Um, First of all, we were to simulate the experiment of tossing a fair coin n times, where n was equal to 5, 10, 20, and 50. Next, we were supposed to simulate repeating the above experiment m times using m as 1,000 n, 10,000 n, and 100,000 n. Next, for each combination of m and n, we computed the probability of heads and tails, and then we repeated those above computations using an unfair coin with a probability of a heads being 0.52, 0.55, and zero point 0.6. So my first step was to write a function that simulated tossing of a coin one time. And to do that, I used the random module. And with the random module, what it does is it randomly generates a number between x and 1, and it does not include 1. It's 0 is less than or equal to x, which is less than 1. And so how I use this for the probability is that if x was less than the probability, I'd have it return heads, else it'd return tails. And that way I could control the probability because if x was less than like 0.5, it'd return a head, 0.5 for tails. But if x was less than like 0.6, then anything up to 0.6, like 60% of the possibilities, were going to give me a head in favor of heads. So that's how I use the probability in favor of heads, which is what we were doing for this project. So that was for simulating the coin toss one time. My next step was to write a function that simulated tossing of the coin multiple times. And to do this, I decided to use dictionaries. And first I set up, I initialized a dictionary to 0 with heads and tails as my key values, and I gave them a value each of 0. And then I said for I in range n, where n is how many times we're going to toss the coin, which is 5, 10, 20, or 50. And then I said f is equal to flip of p, and flip is my one coin toss function. So for each of those tosses of n, I'm going to flip the coin with my one toss function, and that's going to give me either a heads or a tails. And then for whatever those values are, I increase the value in the dictionary by 1. So toss of whatever the flip function gives me will be increased in the dictionary by 1. And then I return toss. And that way now I have a dictionary for however many repeatings of n that I have. I'll have so many heads and so many tails. Next, I wrote a function that repeated the n toss of a coin m times, where m was 1,000 n, 10,000 n, or 100,000 n, and for each of the possible outcomes, I put it into a dictionary that kept track of the number of occurrences. And to do this now, so I kept large M as 1,000, 10,000, 100,000, just for bookkeeping purposes, because later on in my output chart, I'm going to use M, and that was an easy fix. M is just M times 1,000, so that's what I did on the first line. And then I initialized an empty dictionary, which I called outcome. And then for I in range n plus 1, I set values of outcome equal to 0, outcome of I. So I, just by observation, saw that for every possibility of n, like whatever number it was, I always got n plus 1 possibility. So if I tossed a coin 5 times, I would have 6 possibilities because like the heads could be 0 through 5, so 0, 1, 2, 3, 4, 5, and that's 6 possibilities. So I first initialized my dictionary and set it to 0 for all those possibilities. And then for I in range M, which is the how many times we're repeating it, 1,000 n, 10,000 n, 100,000 n, I was going to use the multi-flip function, which will repeat that n, will repeat the n toss, and it'll give me a dictionary of heads and tails values for like the 5 toss or whatever n is. And then you see below that h equals r of heads. And I do that because I really only care about heads. I'm keeping track of how many heads I get out of all these possibilities. So I look up the value of heads in that multi-flip dictionary, and then I increase the outcome of that value in the outcome dictionary by 1. And why I did that is because I have this outcome dictionary that I've already initialized to all of the possibilities. So whatever I generate within the multi-flip function, however many heads I have, it's going to already exist within the outcome dictionary. I'm just trying to keep track of how many times I get that outcome. And so I look it up in the dictionary and set the value. I increase the value by 1 and then return my outcome here. And so and then step 4 was to write out a function that prints the probabilities of heads and tails for each combination of M, N, and P. So here I had to take that outcome function that you saw previously, and for each of those outcomes I need to calculate the relative frequency of the event, which is the probability, and that's just going to be the outcome that I generated in the outcome dictionary divided by the total number of outcomes. And I'll do that later on, but that's how I get the probability. But first of all, once again, m equals m times n, and then the sum equals 0. So I initialize the sum accumulator to 0, and I do this because I'm going to sum up the total possibilities, which those probabilities or the relative outcome, should all equal 1, like 100% of the probabilities or the outcomes. So that's why I have a sum accumulator. And then I print a bunch of dashes, print the number of tosses, dot format, number of tosses, which is going to be 5, 10, 15, or 20, 50, and then the number of times the experiment was repeated, probability of a heads, probability of a tails, more slashes, and then, heads, tails, probability of events. And then here I call out the outcome function, and I set it to variable outcome, and that just makes that dictionary available to this function. And then I said L equals list of outcome.keys, and that's just to get an iterable list of the keys of the dictionary outcome. And the way that I set it up is I initially had it so it's 0 heads, 1 head, 2, 3, 4, 5, but the way that the format output I'm trying to copy was set up, it goes 5. So I had to do, it goes 5, 4, 3, 2, 1, 0. So I had to do an L.sort reverse equals true, which just reversed my combination so that I had 5, 4, 3, 2, 1 in my dictionary, in my output. And then I said for key and L, so I'm going to iterate through these keys now that have been put in the order that I want them. And I'm going to print, which is dot format, the value of the key, which will be the number of heads, n minus key now, which is going to be tails, and then the outcome of key over m, which outcome of key is the number of occurrences of getting a heads, is what I was looking at, and then you divide it by m, which is the total number of occurrences. And so that's going to give me the probability there. And then underneath, sum equals sum plus outcome of key over m, which just says that if outcome of key is the number of occurrences of that event, and then dividing by m is over the total number of occurrences, and that's my relative frequency, then the sum of all the relative frequencies or probabilities should be 1. And that's what I'm keeping track of in that sum there, and then I show the sum. And then this, well, I'll come back to this because that explains. So now I'm just going to show you my code here that was in my PowerPoint presentation. But this is just, wait, that's my, this is my actual code as you see it in Python. So here's my flip for one coin toss. Here is my multiple coin toss where I generate a dictionary that tells me how many heads and tails I have out of n tosses. And then outcome will just give me the multi-flip for repeating it m times, and it sets up dictionary to count how many times out of those m times, out of the n times you got a heads or a tails. And then this format statement here prints out the outcomes in a nicely formatted table. And the output of that you see here. And I'm just going to grab the probability outcome predicted, which is it uses the mathematical formula for predicting probabilities. And so I'm just going to show you a comparison here. So this is for 5 coin tosses with a probability of 0.5, getting 5 heads. My simulated probability is 0.0302. The predicted probability is 0.312. You see 0.16, 0.15. It's very close. And the next one's 0.52. Let me find that. So 0.52. Let's see, I have 0.036. It says 0.38. 0.17, 0.175. You see it's very close. 0.0254, 0.02548. But let me show you now the error outcome here. And then I'll show you how I calculated the error. 1 second. Let's write this down. So that's my error. Final project output. Okay, so my error now, you can see that for the 5 tosses 1,000 times, the predicted probability is 0.31. The simulated probability that I got is 0.029. That's an error of negative 0.00185. And my percent relative error is negative 5.925, which isn't that far off. You know, once again, they're all pretty small. But where you start getting larger percent relative errors is down here for like 20, where my simulated probability was 0. Predicted probability is 9.537 times 10 to the 7th, or negative 7. And that's a negative 100% error. And at first that really made me worry, but since percent relative error is predicted probability minus the simulated probability over the predicted probability times 100. Since my simulated probability is 0, the predicted probability divided by the predicted probability is going to be 1, and that's how I get it, times 100% error. But that's just because we're dealing with such small numbers. And also, for each event, you have like the probability of getting like a heads is 0.5, and you raise that to see the 20th power. So 0.5 to to the 20th is 9.53 times 10 to the negative 7th. So that's there it is. Probability of getting this outcome, which is very small. So you're going to have to toss this like a million times to try to get this once. And you can see that I didn't get it at all because the probability for this event is so small. So it makes sense since I've only done it 1,000 times. I'm not going to get any in all of these occurrences. These probabilities are a little higher, and I actually, had some outcome in those areas, and that makes sense that my percent relative error is smaller. And as we get higher into 50, it's always these outer outcomes, which is 0.5 to the 50, 8.8 times 10 to the negative 16. I don't even get any results in that area because it is so small. Once again, only did it 1,000 times, so that makes sense. For 10,000 times, well, I still didn't get any, but if you look at the well, there it is. If you look at the probability outcomes predicted for the larger like ends of 50, it's also 0 because those outer outcomes, it's 0.52 raised to the 50, it's very small. So even though this mathematical calculation for probability, even that gets it at 0, even though it does it like a million times. So this is my my error, which is very close. It's just the relative error is so small that makes sense. And then so how I calculated the relative error was I used the mathematical formula that my teacher used, which is n factorial over m factorial. So n factorial is the probability or the number of times that experiment was repeated over m factorial, which is how many times you got like a head or whatever, and then n minus m is like tails in this case, and then you're gonna multiply it, which is done down here by the probability of getting a heads raised to how many heads you got, the probability of getting tails raised to how many tails you have, and so I used that down here in my error. So I kept the same formatting, and you can see down here that the error was calculated to be the outcome of key over m, which, as you remember, is my simulated probability. That's my outcome looking in for key, how many times I got heads over the total number of occurrences. So that was my simulated probability, minus the predicted probability, which uses these mathematical equations that I imported. I just kept it here, commented it out so that you can see. And so that will be my error, is the simulated probability minus the predicted probability. And my percent relative error then is that error, the simulated probability over the predicted probability, divided by the predicted probability, which is this function probability of head and key p, which I imported, and then I multiply that by 100 to give me my percent relative error, and then I have it nicely formatted in a format statement here, and this is a nested loop to print it out. And so that is what gave me my percent relative errors here. And then so for I just want to discuss how I can use my results to judge a coin to be fair or not. And for a fair coin, you could see that the distribution of the probabilities was centered around the average or the mean of the results, which for like the 5 coin toss was 3 heads, 2 tails, and 2 heads, 3 tails. And so the distribution looked like a normal distribution curve or like a bell curve, and it had very symmetrical data. So it was very obvious that it was a fair coin because it was all symmetrical. So the probability for 0 heads, 5 tails, and 0 tails, 5 heads was pretty identical. So it's 1 heads, 4 tails, or 1 tail, 4 heads, and then 2 heads, 3 tails, 3 heads, 2 tails. So it's very symmetrical, which created that normal distribution curve or like a bell curve. Um, and so you can tell it was a fair coin. However, for an unfair coin, you don't see this same equality of probabilities. Um, for an unfair coin, if the coin is biased towards heads, the distribution of probabilities is shifted in favor of more head probability outcomes, or towards the side of all the heads and 0 tails. So you could see that the data was no longer symmetrical, but was shifted for me to the left, which was like 5 heads, 4 heads, like the more head probabilities. So it becomes kind of obvious that you no longer have a fair coin, and I can show you that in the predicted probabilities. So you can see here the data is very symmetrical. 5 heads, 0 tails is 0.03125. It's exactly the same for 0 heads, 5 tails. 4 heads, 1 tail is 0.156. Same for 1 heads, 4 tails, 0.156. And then 3 heads, 2 tails is 0.3125. 2 heads, 3 tails is 0.125. You see it's very symmetrical. This is a normal distribution curve. Very easy to tell, symmetrical data, 0.5 probability for heads, 0.5 probability for tails. It's pretty obvious that's fair. Now here for an unfair coin, 0.52, you see how it's no longer symmetrical. It's been kind of shifted this way to the left, which favors the heads. You can see that even more here, 0.05, 0.25, 0.33. It's shifting, 0.33, 0.27. It's been shifted over this way to the left towards the greater head possibilities. Same here. Let's go to like a few more with more outcomes. Actually, it's harder to see. We'll just see it here. But yeah, you can tell it's been shifted to the left. So it's more obvious that it's no longer a fair coin. And so I'd use those results of unsymmetrical data to tell if a coin is fair or not. So yeah, that's my final project, the coin cost simulation. Thanks for listening. I hope you enjoyed that.